All right, guys, and welcome back. We're here with chapter 15, which is titled Chemical Equilibrium, and this is going to be a great start with the lab that is currently in cycle right now with the heat of reaction lab. You guys are learning about temperature changes and recording them, and the relationship between a change in temperature and the amount of heat energy it's giving off. So chemical equilibrium, at least the beginning of this chapter, is really about heat as energy, right? And sort of tracking and measuring that heat energy. We do that very easily with some pretty complicated and some also pretty basic types of equipment here. One's known as a calorimeter, and the other one's just a basic coffee cup that a handful of you guys have actually already seen in your most recent lab, right? Coffee cup, aka little styrofoam cup. So a calorimeter is an insulated device used to measure the amount of heat absorbed or released during a chemical reaction or a phase change. Right, so obviously chemical reaction is going to be the emphasis here, particularly regarding our most recent lab that we've been doing, the heated reaction lab, because you guys ran you're going to run three different chemical reactions, in your little styrofoam cup there, and kind of measuring the amount of heat absorbed or released, right? And we're going to be able to do that just by basic recording of temperature, either going up, going down, and anything in between. Okay. Some characteristics of a calorimeter are going to be things like all heat from the reaction or phase change is transferred to the water. So we're specifically looking at this calorimeter in the top right-hand corner, known as a bomb calorimeter. So the ignition terminals basically start the reaction here. Your sealed reaction chambers in the dead center here, where you've got your substance. And then everything else in between or around it is a secondary chamber with all the water and everything on the inside surrounding it. So all of the essentially the change in temperature that occurs here is measured from the water here, right? So any increase or decrease in temperature based on the reaction happening inside of that little sealed chamber there in the center is going to impact the temperature of the water, which will then be recorded using this thermometer here. And you're able to sort of measure that temperature change. Again, the great thing about these different types of calorimeters, the more expensive and the more intricate they are, it really does a good job of sealing in all of that change in temperature, right? So if you're creating a lot of heat, essentially, a lot of heat energy from your chemical reaction, it's going to have a hard time escaping into the surroundings, okay? So example, okay, a very, very basic calorimeter I was just talking about, right? A coffee cup is used in lab as a calorimeter, right? So coffee cups have some really good insulation to them, very, very basic form of insulation. It's going to be very useful for us when we go to actually measure the changes in temperature we're doing for our upcoming lab. Now, again, a majority of the beginning of this chapter is all based on this idea and concept known as thermochemistry. Now, thermochemistry is the study of the energy changes that accompany chemical reactions and phase changes, guys. Any kind of chemical reaction and really any phase change, which we actually kind of already learned about last chapter, they all incorporate some kind of change in energy. Right, and so again, in essentially the type of energy we're talking about is heat as energy, right? Heat as energy. Now, of course, when you think of the word heat, you might be thinking of temperature, but again, remember, temperature is the measurement of the average kinetic energy. Kinetic energy is the movement of the energy of movement, right? So heat energy, energy of movement, not entirely the same, but you are able to pretty accurately sort of scaffold. If you're able to measure the temperature, you're able to eventually, with some calculations, determine the actual change in energy as well, right? Specifically heat energy. So knowing the temperature is one thing, and that's great, but being able to use that change in temperature to help us calculate change in heat, awesome. Another thing that we're going to learn this chapter here, right? So 3 areas we'll talk about in thermochemistry that we have to be really, really consistent in terms of knowing what they are. The first thing is called the system, right? So this is very, very specific vocab here we have to really, really lock in on, okay? So system. It's the reaction being studied. So anytime you guys perform a chemical reaction where you are trying to measure temperature changes, right, starting versus ending, right, initial versus final, the actual reaction taking place is the system itself, all right? Next up is surroundings, right? Everything in the universe other than the system, right? So genuinely, guys, when we talk about, the reaction being studied being the system, right, your chemical reaction you're actually doing in front of you, everything around it, right? The surroundings, the immediate surroundings, the desk that the reaction is being run on, the lab bench rather. Again, the air around it, the room that you're in my chemistry lab here, right? So all of the things surrounding the actual chemical reaction, the system, that you're kind of doing here, that you're studying, is the surroundings. When you put those two things together, system plus surroundings, you get what's classified as the universe, right? It's just a basic summation of your system plus your surrounding here, okay? So there's really not much to write home about regarding these, okay? But again, knowing how to utilize these three vocab words, system, surroundings, and universe, is going to be really, really important when it comes to some of the stuff we talk about. Now, why is that important? I'm going to kind of show you a little bit of a diagram here, right? So we got three different arrows in this little diagram here with a little vial of a green liquid, green solution, and a reaction occurring, and a box around it, okay? So if we take a look at this very first arrow here is going to be considered the system, right? The system is going to be, again, the reaction taking place, what we ourselves are viewing and we are essentially studying, right? So again, the system is the reaction being studied. So we ourselves are studying this system here, right? Now, it's inside of this box here, which we would be then considering our surroundings, right? So the surroundings is going to be, everything around it, right? Depending on how you are measuring, right? Depending on how you are studying the actual system, by the way, right? The system could either be just the contents of the flask and the flask, or just the contents of the flask. So if you're studying the system in terms of it just being the contents of the flask, right? The green liquid here, you would then be able to determine that your surroundings might change a little bit, right? Because if you're studying the flask and the contents, the flask would become the system and no longer become the surroundings. But if you're studying the system as just the contents, right, the green liquid, then your flask would actually be the literal, at least part of the surroundings, right? So some things to keep in mind as we talk more and more about these systems and surroundings. And again, the combination of both those things is going to be the actual universe, right? System plus surroundings equals universe. Now, heat of reaction, right? The actual core of what it is we're trying to explain here. Right, this new vocabulary word here called enthalpy. Enthalpy of reaction is the change in the thermal energy for a chemical reaction. All chemical reactions, guys, have some amount of enthalpy or heat change, right? This is a new type of sort of measurable unit we're going to be talking about here, right? In a different unit called joules. And the symbol we're going to be using here is symbol H, right? So whether heat is being absorbed or released in a reaction, and again, we're going to be using the symbol of capital H here to help us out with this, right? So this little delta H symbol here is going to be called the enthalpy change for a reaction. This is going to be something that we see pretty consistently. It's going to also lead to a new part in our reference table we're going to be looking at very soon. So we'll keep a lookout for that. Now, there are two really, really big, massive, incredibly important vocabulary words here I'm about to talk about. One of them is on your screen right now, called the endothermic reaction, where heat is being absorbed or entering the system, versus an exothermic reaction, where heat is being released by the system or exiting the system, right? Now, there's two additional things on here, this delta H here and delta H here. For all endothermic reactions, where heat is being absorbed and entering into the system, the delta H value you're going to eventually calculate or view or witness, whatever, or record, is going to be a positive value for delta H. Versus for exothermic reactions where heat is being released or it's exiting the system, okay, it's going to be a little bit of a different story here. This delta H is going to be exactly the opposite of it, right? It's going to be a negative delta H value regarding our exothermic reactions, okay? And we talk more about these types of things, these different types of reactions here, endothermic versus exothermic reactions. We're going to talk pretty specifically about, what it means by heat is absorbing or entering and heat is being released or exiting a reaction, right? And what I mean by that. Now, like I was saying before, we've got a new table to talk about here, okay? Table I, which is your heats of reaction at 101.3 kilopascal and 298 Kelvin, right? A couple of measurements we've seen not too long ago. 101.3 kPa or kilopascal is going to be our standard pressure, and 298 Kelvin is actually not going to be standard temperature, so this is not at STP. 298 Kelvin is actually going to be approximately it's going to be exactly 20 degrees Celsius, but again, when I say approximately, it'll approximately be room temperature. Again, room temperature is usually anywhere between 20 and 25 degrees Celsius, depending on what it is and how you're measuring it. Now, when it comes to table I here, there's some pretty specific units we're going to be taking a look at, right? Everything measured here on table I is in kJ, or also known as kilojoules. K being kilo, 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 and capital J here being the unit for joules, right? This is not the first time we talked about a unit of energy called joules, right? We actually did this way back at the beginning of the school year, actually, in chapter 3. We talked about heat energy very briefly, and kilojoules was actually mentioned back then. Now, again, when you look at, and I'm going to actually specifically look at a couple of these measurements here, right? Here's one, for example, here, right? This is a value in delta H, right? A value, rather, with a unit of kilojoules, where we are measuring this delta H value here, where the delta H value is a negative, right? So, in this case here, the negative delta H means that this type of reaction is resulting in an exothermic reaction. Whereas on the flip side here, if I were to erase this stuff here, on the flip side here, if we're going to look for a positive delta H value like this one right here, right? This value here measured in 182.6, right? Positive 182.6 kilojoules, right? So a positive delta H value means we are resulting in an endothermic reaction. So this is what I was talking about not too long ago, where I was specifically mentioning positive and negative values for delta H, determining, and allowing us to determine if something is an endothermic or exothermic reaction. Now, the amount of heat energy, right, these delta H values here are based on the mole ratios on this table I here, right? When I talk mole ratios here, we have to be thinking about exactly what we did not too long ago, right? So, for example, let's look at this one right here. Okay, this example right here. Okay, we have a mole ratio of 4 to 3 to 2 for this reaction of aluminum and oxygen, resulting in aluminum oxide here, right? So if these mole ratios were to change, that would result in a change that is exactly the same for our delta H value here, right? Our delta H value here is negative 3,351. So if we suddenly saw a doubling of these mole ratios, right? 4 being doubled or multiplied by 2 to give us 8, 3 being doubled to give us 6, and 2 being doubled to give us 4 here. If we were looking at some kind of example problem where our mole ratios were 4, 6, or 8, 6, and 4 respectively, this would actually also result in a doubling of our delta H value, right? So 3,351 would turn into, if I grab my calculator real quick, we can figure this out, right? Negative 3,351 times 2 gives us a value. I'm going to squeeze it in right here, negative 6,702 kilojoules. I'm writing this all out with my hand on my mouse here, so a little bit more difficult, but again, still rings true here, right? So again, the doubling of your mole ratios is going to result in a doubling of your delta H value as well. Okay, so pretty important stuff to know and recognize here. And that's going to be the end of the video today. We're going to talk more about this stuff, do some examples of it in class, and I'll see you guys then.